without further ado, it's a great pleasure to introduce Will Sawin of Columbia University, who's going to talk to us about the Bateman-Horn conjecture over function fields.
Thank you. Yeah, so everything I'm going to talk about today is joint work with Mark Shusterman, and it's also work in progress. So hopefully it'll be done soon, but the exact numerics in statements might change somewhat. So they told me that for the purposes of this seminar, analytic number theory counts as additive combinatorics. So I'll begin with some classical analytic number theory. So we're going to take a polynomial, g over the integers, and we're going to plug in integer values and ask how many of these are prime. And the classical conjecture of Bunyakovsky is that infinitely many of these are prime, except if there's some kind of clear obstruction. And so if G is a product of two different polynomials, it will almost never be prime because everything will be a product of two factors. If G takes only finitely many positive values, it will also only take finitely many prime values because primes are positive. And the last thing is there could be some congruence obstruction. If all the coefficients are a multiple of 2, or if we have some polynomial like x squared plus x plus 2, where the coefficients are all multiples of 2, but all the values are multiples of 2, in this case, since very few multiples of 2 are prime, we will not have infinitely many primes. So this conjecture is very hard. Only a few cases are known. If you plug in a linear polynomial, this is equivalent to Dirichlet's theorem on primes and arithmetic progressions. But that's the only case that's known. We don't know for any other polynomial. So for example, you would take x squared plus 1. We could make the conjecture as infinitely many primes of the form n squared plus 1, which is itself a classical conjecture. And so in number theory, when we have a really hard conjecture that we don't know how to prove, what we can often do is just make an even stronger conjecture, which is even harder to prove. And so in this case, that is the Bateman-Horn conjecture. And basically, the reason for this is just saying that there are infinitely many primes is not so precise. We would like a harder quantitative statement about the number of primes in a given interval. So it's natural to take the quadratic interval between x and 2x for a real number x. And then we count the number of n in that interval such that g of n is prime. And then we again will get it as kind of a product of a bunch of reasonable factors. So we start with x, the number of natural numbers in the interval, and then we put the probability that each individual number is prime. So for a natural number of size x, that would be log 1 over log x, because g of n will have size x to the degree g, we have a log x times degree g. And then we have a product over prime p of these kinds of congruence factors. So we count the number of x mod p such that the g of x is not 0 mod p, since all but 1 primes are not 0 mod p. And then we divide by the kind of expected number of x, such that g of x is non-zero mod p, which is p minus 1. And so this kind of product formula gives us a reasonable conjectural prediction. And then we predict there'll be a lower order error term. And then we still need to make some assumptions of a polynomial. We need to make some kind of positivity assumption in irreducibility. So I could define negative numbers to also be prime, which would mean I wouldn't need this positivity assumption, but then the Euler product wouldn't really make sense. So negative numbers are not prime. So this isn't, what I stated is not the most general form of Bateman-Horn conjecture. There's an even more general form where you look at a series of polynomials and you want to know that they are all taking prime values at the same n. I want to know how often they all take prime values at the same n. And so this conjecture is a big generalization of the Hardy-Littlewood conjecture on prime tuples. but I don't have anything new to say about that conjecture today, so I'm not going to discuss it further. So the other thing we can do when we have a very hard problem in number theory, or one of many things we can do, is we can consider the analog for polynomials over a finite field. So here we're going to fix a finite field FQ, which you can think of as integers mod p, or an extension of integers mod p. And then we're going to look at the ring of polynomials in one variable over a finite field FQ. And we're going to think of that as a model for the integers. And so we need to define, to do that, we need to define the kind of the same concept. If we look at the concept of a prime polynomial, a prime integer, we're going to define the analogous concept of a prime polynomial. And so we will say a polynomial is monic if its leading coefficient is 1, which is kind of the analog of positive. And we say a polynomial is prime if it's monic and it's irreducible. So it's not constant, and it's not the product of two non-constant polynomials. And then we can make an analogous conjecture. And so we are going to replace in this conjecture the integer, the interval x or 2x, the quadratic interval in integers, with the set of all polynomials which are monic of degree d. If you think about this purely additively, the polynomials which are monic of degree d are like a vector space over the finite field FQ. And so the additive model of vectors of integers modeled by vector spaces is something that is used often in additive combinatorics and was discussed previously in the seminar. It showed up in Tom Bloom's talk, I checked. And so this is kind of the analog of that, where we're also using the multiplication structure as well. And then we can make a conjecture, which is almost exactly a point-by-point analog of the conjecture we made in the previous slide. There's just one difference. So we take, again, the number q to the d of polynomials, monic of degree d, and we, again, multiply by the probability that an individual polynomial is prime. So the prime number in here for polynomials tells us the probability of polynomials prime is 1 over the degree. So we'll take 1 over d times the degree of g. And then we take a product, we take the same kind of Euler product, which is now a product of prime polynomials of the number of residue classes modulo that polynomial, such that g of x is non-zero mod that prime polynomial. And then we again divide by the expected number, which is q to the degree of pi minus 1. And so this is a reasonable conjecture, but we have to put some conditions on it. So we again want g to be an irreducible polynomial, and we have this kind of positivity condition. The right positivity condition is that the leading term in x is monic in u, because that will ensure, if we plug in x for g of ux, so our polynomial, we have a polynomial in one variable whose coefficients are polynomials in one variable. So it's a polynomial in two variables. And we're going to plug in f for one of this variable and ask when it's prime. And so we want that to be monic. So we need some condition on g. Well, there's one weird condition, which I'll talk about later, which is that we want g to not be a polynomial only in x to the p. So if I look at all the terms in x, and I look at all the exponents, they should not all be multiples of p, where p is the characteristic of fq. So fq is an extension of z mod p. And so this condition is because of a phenomenon that occurs only for polynomials over a finite field and not over the integers. And I'll explain more about it later. So this conjecture is almost as hard as the conjecture of the integers, but it's not quite as hard. So we can actually make some progress in a case of this conjecture, which was not known over the integers, the case of quadratic polynomials. So we'll take g of x to be x squared minus d. And we will get kind of the expected statement. So the assumption we need on D is that D is not a perfect square. And then we're counting the number of F's, which are monic of degree D, such that F squared minus D is prime. And we get the expected number. So this is Q to the D divided by the degree, which is 2 times D. And then we have the same product. I've written out the product. This is we're counting the number of D X, which is not the square root of D, mod pi. But we don't just get that they're asymptotically equal, the number of primes equal to this as predicted by the conjecture. We get an error term which has power savings. And I've written an explicit formula for the amount of power savings right here. It's kind of a crazy formula, but what's relevant about it is that this exponent is less than 1 as long as Q is greater than this cutoff. So we need to assume Q is greater than 96 squared times E squared times P to the 4. So E is not a variable, it's 2.718, and that kind of shows up in the proof. And we also need to assume that P is odd. So nothing I'm going to talk about today will work in characteristic 2, or at least not the same way it does in characteristic 2. Does anyone have any questions about this statement? A little bit. Yeah, well, if you have any questions at any time, feel free to chime in. So there was some prior work on this question over finite fields. So there's been a lot of, partial work on different cases of Bateman-Horn over the integers. But over finite fields, there was work of Pollock. And so Pollock did not prove the asymptotic, but he proved that there exist infinitely many prime values of certain polynomials, where these polynomials would typically have the form like a power of x times minus beta. So he'd be taking a power of a polynomial and adding some kind of constant, and he wanted that to be prime. And then he does this by an explicit construction, so which involves taking f to be a large power view. So his polynomials produced by this are very, very special. We're like plugging in a monomial to a very special polynomial, and we're producing a very, very special polynomial. We can check if it's prime. And so this produces a low density of solutions, but it does produce infinitely many. And then a lot more is known for our polynomials, if we fix the degree D, but let the size of the finite field Q go to infinity. In that case, there are results which give the correct kind of asymptotic formula for function fields in that limit in some special cases. So Pollock handled some kind of special case, and Enton handled something more general, and Kowalski did some work as well. But this is kind of a very different problem. So a key ingredient in improving this is the result on the Möbius function, which basically resolves the parity problem for this. So the Möbius function in the integers is like is -1 to the number of prime factors, or 0 for prime factors repeated. So for polynomials of a finite field, we define the Möbius function the same way, -1 to the number of prime factors, as long as they're distinct. And then you can even, we'll allow non-monic polynomials here. So if you have a leading coefficient which is not 1, you just divide by the leading coefficient, and then you can factor into primes. And if you can't write it as a product of distinct prime factors, so if there's some repeating prime factor, the Möbius is 0. And then Chowla's conjecture over the integers says if you take a polynomial and plug in integer values, the average of Möbius over this polynomial should cancel always, unless it's like a perfect square. Right, I guess I should say G is square free. Or no, yeah, if this is perfect square, then Möbius is always 0, so it's okay. And then we have an analog of the shallow conjecture for polynomials. So we're going to again pick a polynomial G over with coefficients in FQ adjoin U. So a polynomial in 2 variables over FQ, and let K be the degree in X. And then we're going to sum the Möbius function of G over GUF over monic F of degree D. And we're going to get cancellation in this sum, which is, so the length of the sum is Q to the D, and we're going to get a sum which is less than that by some kind of factor. And this is always strictly less as long as Q is greater than 4 times K squared times P squared times E squared. So the degree of polynomials we can show cancellation in depends on the particular finite field we're working in. And then it's again crucial here to assume that G does not depend only on X to the P, so that there are some exponent which is not a multiple of P. But under these assumptions, and we still need to assume P is odd, under these assumptions, we have some kind of uniformity in G. So the constant depends only on the degree of G in U, and we have some explicit dependence, which will let us show cancellation even as the degree is growing. And this is something that's very important when you want to actually use it in a number theoretic context. Does anyone have questions about this? Again, feel free to ask. So let me say something about the prior work. And in particular, let me explain why I have this condition. The polynomial does not depend only on X to the P. And the reason for this is that there's some prior work of Conrad, and Gross in that case. And they showed that the Möbius function behaves very differently. So if I take a polynomial of this special form and I plug in f and take the Möbius function, then I get a function of f which behaves very differently from how we normally expect the Möbius function to behave. In basically every situation in number theory, it behaves quasi-randomly, but here it actually behaves periodically. So what I mean by a periodic function on integers is a function that only depends on the convex class mod n. So a periodic function of polynomials, I mean it depends on the convex class of f modulo some fixed polynomial n. And it also can depend on the degree of f mod 4 because of some weird sign factors that show up. So if you're summing a periodic function over a very long interval, it's kind of straightforward to see if it cancels. You just add up over all the residue classes mod n, and if that's 0, then your sum will cancel in the large n limit, not large, in the large interval limit. And if it's non-zero, then your sum will not cancel in the large interval limit. And they basically evaluated these sums, and sometimes they cancel and sometimes they don't. So the behavior of Möbius sums when there is this p power showing up is just like fundamentally different. And so we're handling the case of all these polynomials which are not in the special form, so not handled by Conrad. But one thing that's maybe surprising about this is we are going to basically be using methods from their paper, and we're going to be basically reducing to that case to prove these kinds of theorems. So we're going to be substituting our polynomial as like r plus s to the p, where r and s are two other variables, and we'll try to show cancellation of the average over s, which means that our polynomial will have this special form, and the Möbius function will be periodic. And then we'll try to show that for most values of r, this periodic function will cancel over the interval we're summing it over. So this is sort of different from the approach by Conrad, and Gross. So they use the fact that Möbius is not random and is periodic to kind of adjust Bateman-Horn. They realized that the Bateman-Horn conjecture was wrong for these special polynomials because you should have extra terms coming from these Möbius sums. And so they use it to kind of like correct the conjecture and get a statement with massive numerical data. But we're using this to actually prove cases of the conjecture. And so just like in the previous case, there was work also in the Q to infinity limit. And the Q to infinity limit, these problems are like very closely connected. The Möbius and the primes, sort of even more closely connected than they are with the integers. And there was work of Carmon and Rudnick in the case where G is a product of linear terms, which is like the case of child conjecture people most often study. And there was also some work of Entin. So I'm now going to say something about the proof. So in writing this talk, I don't know exactly like what kinds of background material people in this audience are familiar with. And so I wrote it to make some assumptions. But I think almost certainly if there's anything in here you're not familiar with, it's going to be very close to something that you are familiar with. So please ask questions, and there'll hopefully be a very good explanation, except on the very last slide, where I can't make that promise and all bets are off. So the actual proofs that are in this work in progress are quite long, and I can't really summarize everything that goes into it. So I'm going to try to talk about one part that I think is interesting, in particular because it relies at the end on some classical topic in number theory, which is the deduction or almost deduction of theorem 1 from theorem 2. So of Bateman-Horn from Chowla in this setting. And so let me phrase the question, is our Chowla statement strong enough to imply Bateman-Horn? So let's kind of open it up and see. So we're going to do the same thing we sort of always do in number theory when we want to count primes. So just immediately switch from counting primes to the von Mangelt function. So the von Mangelt function in F2 adjoin U is just defined to be if F is a power of a prime pi, von Mangelt function is the degree of pi, and otherwise it's 0. So it essentially is the same as counting primes. So what we're going to need to do is to sum over F monic of degree D, von Mangelt function lambda of F squared minus D. And then what's convenient for us about the von Mangelt function is it has a close relationship to the Möbius function. We can write the von Mangelt function of F as a sum over divisors G of F of Möbius of G times the degree of G with a minus sign in front. And so these are the exact same formulas you'd see over the integers, except you would put a log here instead of degree. And you probably would use the letter pi to represent the problem. So in fact, most of the calculations I'm going to be doing, you can just pretend that these are integers instead of polynomials. And I considered even writing like both the polynomial versions and the integer versions on the slides, but I decided that that would be a little bit weird. And also I didn't want to write all the boundaries of like static intervals and things and deal with smoothing or whatever. But you can just pretend these are integers if you feel like it. And then at the end, we'll see why polynomials and integers actually behave differently. So if you just plug in this von Mangelt formula into the sum, and you fix the degree of G. You can handle each degree of G separately, and then you don't have these degree G terms. You get the sum over F, degree D monic, and the sum over G dividing F squared minus D of the Möbius function of G. So this is the sum we're going to think about for most of the rest of this talk. So I'll write the sum again. And we can think about what happens for different values of n. Like what happens when the degree of G is small, what happens when the degree of G is large. So m is small is actually the easiest case. Because when m is very small, what you can do is you can switch the order of variables so that you're summing over the degree of G first. And then the sum over F looks like we're summing over F such that F squared is congruent to D mod G. And that sum, it only depends on the convex class of F mod G. And because the degree of G is less than D, there's like an equal number of possibilities for F in each congruence class. So you just get a sum over residue classes mod G. And then if you factorize G into a product of primes, you can factorize that sum. And you get like an Euler product. And if you manipulate the Euler product a little bit, you get the formula we gave for the main term. So this range gets you the main term. There's a little bit of error term that comes from this range, but it's very, very small. And this is kind of straightforward and classical argument, which is when M is small, the degree of G is small. So in the case where M is large, we need to kind of flip things around to find the variable that's small. So we're going to set H to be F squared minus D divided by G, because G divides F squared minus D. And so the degree A of H is 2D minus M, and the degree of H will be very small. And because it's small, it's helpful to fix H first and try to get cancellation and sum over everything else. So we have this equation F squared minus D is equal to H times G. And then we can think of that in terms of the residue class of F mod H. The residue class of F mod H must be the square root of the residue class of D. So we'll split into residue classes mod H. So I've done in this equation what I told you to do in words. We're summing over H first on the outside. Then we're summing over residue classes mod H, which satisfy this congruence. And then we'll sum over F, where F is congruent to alpha mod H. And then we'll finally sum over G, where GH equals F squared minus D. And then here we can do kind of a change of variables. Because F is congruent to alpha mod H, we'll subtract alpha and divide by H and get a new variable F twiddle. And then we can express G in terms of F twiddle. We write F as HF twiddle plus alpha, and we square it and we subtract D, and we get this kind of formula. And so now we get a sum of Möbius that looks exactly like the kind of sums we're bounding in the Chalice conjecture. Möbius of a polynomial in F twiddle, which itself is of degree D minus 2D minus M, or the same thing as M minus D. So the amount of cancellation we can get in this sum over F is going to be exponential in M minus D. And we also will have some kind of loss from the uniformity. So we're going to be in good shape as long as M minus D is sufficiently large. But if M minus D is very small, like 1 or 2, or like square root of D or something, then we'll be in trouble. And then the amount, the cutoff for how small M minus D can be is getting better and better as the finite field FQ grows with fixed P. So we can always take Q large enough to make the cutoff small enough, though we only need to really consider the case where M is only a tiny little bit more than D. But outside that case, we can apply theorem 2 and can conclude a power savings estimate. So the worst case for us is when M is slightly larger than D. And at first I thought there's no way that we could handle this case. But in fact, it turns out that we can. And it uses this kind of classical theory of quadratic forms that almost entirely or almost entirely goes back to Gauss. So here I'm now going to pretend that everything are integers when I'm explaining it. And so if we're thinking about a pair of integers f and g, we're counting with g divides f squared minus d. And so you could, for instance, think about an integer that divides f squared plus 1 for an integer. And there's a classical theorem of integers that divide f squared plus 1, which is those integers are always sums of 2 squares, which are relatively prime. And vice versa. Any sum of 2 squares, which is relatively prime, will divide n squared plus 1 for some integer. And then there's a generalization of this to higher discriminants d. So an integer g divides f squared minus d for some fixed discriminant d. If and only if g is represented by some quadratic form of discriminant d, or for d. Ignore those factors. And So this is a great start. We can like try to understand and classify the quadratic forms of discriminant D. But it's not quite enough for what we need, because we don't just care if G divides F squared minus D, we care how many F have F squared minus D a multiple of G. But it turns out that there's like a solution to this too. The residue class is F mod G, such that G divides F squared minus D, are in bijection with these choices of representations, X and Y, up to equivalence. So then what we can kind of do is we can first count the equivalence classes of quadratic forms. Each quadratic form has a standard member, unique up to equivalence, or almost unique up to equivalence. And you can count how many ways are G represented, is G represented by a standard member, and sum up over these equivalence classes. And that will tell you the total number of residue classes F, such as G divides F squared minus D. And so that's great, but it's again not quite what we need, because we don't care about residue classes F, we care about polynomials of a specific degree. So another way to say it is ratio F over G. We want that to have degree like D minus M. And so we can think of that as F over G as being like in a small interval, mod 1. But it turns out that you can recover F over G from the representation. And the way you do that is you take these coordinates X and Y, and you just take the inverse of X mod Y, and you divide by Y. And so this is, and that will be actually almost equal to F over G, up to some very small error. And so this is kind of very weird, because you can do a change of variables in X and Y, and you could change completely the particular values of X and Y, but then the inverse of X mod Y divided by Y will barely change at all. I mean, it'll change a little bit, but not very much. So the key step in the proof for this range is to take all these ideas from the classical theory of quadratic forms and reprove them in the setting of polynomials in one variable over a finite field. And you can do this. It turns out things work out relatively elegantly. You have a nice notion of definite and indefinite forms, and the forms in those two cases are pretty similar. There's one thing it was convenient for us to do differently, which is instead of having a single standard representative of each equivalence class, it's actually better to have a few different standard representatives and just remember how many different representatives there are and divide your count at the end by that total. That gives you somewhat nicer formula, as it turns out. So we can just do all that for polynomials, and I'll sort of explain how that helps us. So I've written this sum from earlier. We're summing the Möbius function of G over G, which divide F squared minus D. And we're again going to flip that around. We're going to sum over G first, and then we're going to sum over these residue classes F, which where G divides F squared minus D, and then also the degree of F over G should equal D minus F. And then it should be monic. And so this condition on F over G, you can think of as the condition that F over G should be an interval, and then you can detect that condition by additive characters. So I didn't write the exact correct formula for detecting it by additive characters. There should be some coefficients depending on H. So I just simplified it a little bit. But basically you get a sum with some coefficients of exponential of H times F over G. So you have to think a little bit about what the right definition of this exponential function is for a rational function in polynomials. But it turns out there's like a pretty, canonical definition you can give using the residue at infinity that has basically all the nice properties of the exponential function of integers. So we get some kind of exponential function sum against Möbius. And then we can use our facts about quadratic forms that I told you in the last slide. We can use this sum over G of residue classes F is the same thing as a sum over these standard quadratic forms A, B, C, and pairs x and y, ax squared plus bxy plus cy squared, that represent G, so that they represent a polynomial of degree m. So the degree of ax squared plus bxy plus cy squared should equal m. And so G becomes this, so we put the Möbius of ax squared plus bxy plus cy squared. And then f over G becomes x inverse over y, so we have an exponential of x inverse over y. And so we get a sum that now looks more like a Chalice sum. In particular, if we ignore all the other variables and just try to sum over x, we get exactly the kind of Chalice sum we were looking at earlier, except that we have this additional term, which is exponential. So I don't want to write it down, but we actually proved a more general Chalice statement that handles Möbius averages against certain kinds of periodic functions, like this exponential function, and has uniformity in the period. And so that statement with uniformity is strong enough to fill in this missing case, the critical range, and complete the proof of the Bateman-Horn conjecture. And then this particular weird lower bound for Q as a function of P, there's some weird constant times P to the 4, comes from looking at the degree of uniformity between these two different Möbius estimates and trying to see when the two ranges overlap so we can get a bound everywhere. Okay, I talked somewhat faster than I expected, and no one has any questions. So I'm going to be over slightly early. So I now want to say something about the proof of theorem 2, so the proof of the Chalice conjecture. And I'll say even a tiny bit about the proof of the variant with these exponentials. And so, unlike the previous argument I showed you, where everything we did worked over the integers, here we're going to use a lot of methods that really use the fact that we're working over polynomials over a finite field and not over the integers. And so these methods have two parts. The first part is there's a method that uses the fact that we're doing algebra and characteristic P. And it uses weird properties of algebra that happen when P is equal to 0. And it's mostly elementary. It's going to be a bunch of algebraic manipulations, and there's some elementary algebraic geometry in there. And then the second part is we'll use these very highly non-elementary algebraic geometry methods. We're using like a cohomology theory and the May conjectures and all of that stuff. And so the characteristic P method is what builds on this work of Conrad and Gross, as I mentioned earlier. So I'm going to be kind of more sketchy in how I describe all this stuff. So we have our Möbius sum, Möbius of G of U F. We're plugging in F, where F is a polynomial of degree D. And we can write this as a sum of over R and S of G of U R plus S to the P. So S is going to be a polynomial of lesser degree, of like degree D over P. And the sum over R will be chosen so that each polynomial F gets hit like the same number of times by this as R plus S to the P. And then the thing we get from using and building on a little bit the methods of Conrad and Gross, we get a formula for the Möbius of G of U comma R plus S to the P. And this formula is a function that's periodic mod S. But it's not just any kind of periodic function mod S. It's a very specific and nice kind of periodic function. So it's a quadratic character composed with a polynomial function. So we can derive from R and G. We can define some modulus M. And we have a quadratic character of the group of like invertible polynomials mod m. And then we have some kind of polynomial function w that we plug in the s variable, and then we plug it into chi. And so we get that kind of function. So it's a special class of periodic function that will often show up in number theory. In other cases, it's like a character composed with polynomial. And then we specifically have reduced the problem to summing over over characters composed with polynomial. So let me say something about how that proof will go. I perhaps should have written more of my slides here. The proof relies on relating first the Möbius function to the discriminant of the polynomial. So the square of the product of the differences of the roots. And then this relationship, you can see it in a couple different ways. You can see very quickly the Möbius function vanishes if the polynomial has a repeated factor, and the discriminant also vanishes if the polynomial has a repeated factor. And it turns out that for these polynomials that are finite fields, that's not just an analogy, but there's a very close relationship. And this discriminant is of a polynomial in over a finite field, or any polynomial. You can express it as the resultant of the polynomial and its derivative. It's the product of the differences of the roots of the polynomial and its derivative. And that's some classical fact from polynomial algebra. And then we do the characteristic P stuff. So we write d du of g of u r plus s to the p. We use like the chain rule and the product rule. And we write this as a polynomial in u and r and s to the p. Now you might think that the derivative of s to the p should also show up in that formula. But the derivative of s to the p is p times s to the p minus 1 times the derivative of s, and p is 0, so the derivative of s to the p is 0. So the formula that we get at that point is the resultant of two polynomials in u and s. And the resultant of two polynomials in u and s, and then we're plugging in s, degenerates into this kind of periodic function in s. And that, again, is a kind of classical fact in polynomial algebra that doesn't use the factor over a finite field. And then it's, again, helpful to look to try to understand this, to think about when the resultant vanishes. If you have two polynomials and two variables, and you like graph them, they each define a curve in the plane. And if you plug in s, then the vanishing locus will be like intersecting these two graphs with the graph of s. And so the only way the resultant can vanish is when the two curves intersect each other, and they also intersect the graph of s. And so that only happens in particular when the two curves intersect each other, which is like finitely many points. So the vanishing of the resultant is controlled by these finitely many points. And because you know the resultant is itself a polynomial in the coefficients, if you know where a polynomial vanishes in algebraic geometry, you basically know that polynomial. There's a duality between polynomials and their vanishing sets. And so that is kind of the tool that you can use, and using Conrad and Gross, and we build on it a little bit to prove this kind of formula. So once we have this kind of formula, we get the sum over a variable s of chi of a polynomial in s. And we're summing over a polynomial with degree d over p, which we can think of as being analogous to interval. And so the first thing we could try at this point is to think about, go back to classical number theory again, and think about if we have a sum of this form over an interval, what would we do? And so there are lots of methods in classical number theory to handle these kinds of character sums over an interval. There's like the Polya-Vinogradov method, and there's Burgess's method. But the problem with all of these methods is our interval is too short for any of them to work. if you're summing it over, a character mod m, they can work over a certain power of m, but our interval is going to be too small a power of m for any of these methods to work. So what we again need to do is to sort of ignore the analogy to classical number theory and think of this as some kind of different problem which uses the fact that we're working with polynomials. And in particular, we want to remember that polynomials of degree d over p over fq form a high-dimensional vector space over fq. And this is a geometric structure. It's a structure we can understand using the tools of modern algebraic geometry. And so we want to sort of handle this sum by putting everything into the language of algebraic geometry and kind of using those tools. So we can replace this vector space of polynomials over fq by like some kind of algebraic variety, some kind of affine space. And this function, this character function we're summing, is going to give us a sheaf on this affine space. And there's a general principle of sheaves that the sum of the function associated to a sheaf can be expressed in terms of the cohomology of the sheaf. So we have these cohomology groups, and then we have Frobenius is acting on them. And we need to show that this trace of this operator Frobenius is not too big. And so Deligne showed in Vade 2 the eigenvalues of the operator are not too big. So what we need to do, at least in certain groups, if we don't look at the very high degree cohomology. So we need to do, to kind of complete the argument and show a bound, we need to calculate some sheaf cohomology groups. We need to show that the high degree groups are vanishing, and we need to give Betti number bounds for the low degree groups. And this is something would be a little bit pretty further afield for me to talk about it. But what I want to do is kind of give some idea of what geometry is showing up. So it turns out when we're doing this, it's very important to understand what's the singularity of the sheaf. And the singularity of the sheaf actually has a totally classical interpretation. These are just the polynomials S, where this chi function is 0. So if the polynomial, we're plugging chi of a polynomial, if the value of the polynomial is not relatively prime to the modulus m, then we set chi to be 0, as is usual for dealing with Dirichlet characters in number theory. And so these points, these S where this polynomial is not relatively prime to m, form some kind of singular locus. And if you look at them specifically, you can go through the prime factors of S one by one, and you can go through the roots of W modulo that prime factor one by one, and you basically get the singular locus is a union of a bunch of these sets defined by like congruence conditions modulo prime factors of S. And what that turns out to be geometry is the union of a bunch of hyperplanes in our high dimensional vector space. So we have a bunch of planes intersecting in space in a certain way. And we have to solve some kind of co-logical, some kind of strange geometric problem involving these hyperplanes. And it turned out that similar problems involving an arrangement of hyperplanes were studied over the complex numbers previously by Cohen, Dimka, and Orlik. And we can kind of adapt their method. We just change some things to make it work over finite fields. It's not exactly the same method, but it is involved. And so sort of a key step is making sure not too many of these hyperplanes can intersect at a single point. And so the way in which we modified their method, luckily, enables us to handle not just this chi periodic function, but a few other kinds of similar periodic functions as well. And so in particular, we can handle this term exponential of hx inverse over y. It's sort of, you plug in r plus s to the p, and it looks like a pretty similar term, and then you can handle it as well in this sum. And that finishes, modulo huge numbers of missing details. That finishes the proof of the Chalala conjecture, which is the key ingredient in the proof. Thanks for inviting me to speak.